All right, we're ready for our next talk. This is one of our distinguished papers for OOPSLA 2024. The talk is on Minotaur, a SIMD-oriented synthesizing superoptimizer, and the talk will be given by Zhengyang Liu.
Hello, my name is Zhengyang. So I'm gonna talk about our paper, Minotaur. Minotaur is a synthesizing superoptimizer on LLVM intermediate representation. This is a joint work by me, Stefan, and my advisor, John, again, over there. So I will start my talk with a motivating example. This is an example showing how easy an optimization can be missed. So here is a loop that calculates the differences between adjacent pair of integers. The loop is very simple and it is found in the LLVM library. This library is used by Google Chrome web browser for image scaling and conversion. The Chrome engineers have spent a lot of time ensuring LLVM achieve decent code generation for this piece of code. And let's start by looking at how LLVM compiles this code. LLVM generates this code when compiled with -03 with auto vectorizer turned on. Here, we assume 8 integers are already loaded into a 128-bit vector. And what the code does is that it extracts the element in the even lane in a new register and the element in old lane into another register. Then the program zero extends the result, and finally we subtract those two new values to get the final result. LLVM cannot further optimize this piece of code. Meanwhile, Intel SSE2 extension has this next fused multiply add instruction, PMAD word. The instruction multiply packed 16-bit integers from 2 vectors and then adds the adjacent result together, and finally stores the result back to the destination register. So if we call PMAD word on vector S, and a constant vector containing interleaved positive ones and negative ones, we will get the exact same result as the shuffle, zero extend, subtract version. So in this case, we need a rewrite rule, as this slide shows, to rewrite shuffle, zero extend, and subtract into an intrinsic call to PMAD word. In this talk, we call the slower sequence, or the sequence found in the original program, the left-hand side, and we call the optimized version the right-hand side. The arrow in this in between denotes the refinement relationship. That is, the compiler can replace left-hand side with right-hand side without breaking the code, even when the program contains undefined behavior. In this rewrite, the left-hand side requires 11 macro operations, and the right-hand side only requires 3 macro operations. This rewrite will save us 8 macro operations. Here, a macro operation is a simple and low-level RISC-style instruction to implement more complex instructions such as PMAD word. In this work, we use the count of macro operations as the cost of a code sequence. For compiler developers, coming up with such rewrite rule may be very tricky. So we developed our superoptimizer for automatic discover useful optimization rules missed by LLVM. So our superoptimizer has 5 different parts. So as real-world programs may be large, and the program synthesis cannot really scale up to the whole program synthesis, we developed a SSA-based cut extractor to split the input functions into small code sequences. Our superoptimizer also have an enumeration-based synthesizer, which automatically generates rewrites for the generated cards. The rewrite generated by the enumerator may not be correct at this stage, and the correctness of the rewrite is verified by a refinement checker. Here we use the LLVM checker for this purpose. And we also have a cost model based on the LLVM machine code analyzer, which helps to predict whether a rewrite is profitable or not. And finally, our superoptimizer caches the synthesis result for later reuse. In the following slide, I will talk about each part in detail, and after that, I will show examples and followed by performance numbers. So here, in this slide, I want to talk about our cut extractor. So to limit the complexity of program synthesis, we implemented a cut extractor that split the input program into small cuts. The cut extractor uses a search algorithm that collects the instruction uses the SSA dependency graph. And our extractor supports extracting both control flow redirections and memory operations. And our extraction algorithm stops at a certain user-defined limits. And all the values that is unknown or all the operations that is unknown to the synthesizer or beyond the user predefined depth limit are listed as free variables. Here, setting the depth limit is crucial to the performance of our superoptimizer. And please refer to our paper for our extensive discussion on this topic. And finally, we call each extracted cut left-hand side. And after we split the program into small left-hand sides, we want to find a right-hand side that is a cheaper implementation of the left-hand side. Here, a right-hand side may be a constant, or an existing value found somewhere in the left-hand side, or some new instructions. So we perform a search algorithm. We enumerate all the possible right-hand side up to a certain user predefined resource limit, and in the order of increasing complexity. After we get a left-hand side and right-hand side, we need to check if the left-hand side and right-hand pair is a refinement. Because this is simply because compiler optimization must be sound. We do not want miscompiles. So here we use the LLVM translation validator for this task. To make LLVM be able to reason vector programs, we need to teach LLVM the semantic of those vector operations. And now the semantic for all platform-independent vector instructions, such as trivial add, sub, floating point add, and integer and floating point comparisons are implemented and are already added. And other data movement operations such as insert element, shuffle vectors are also implemented and open sourced at our main LLVM repo. And moreover, I have also hand-coded the semantic of 165 x86 integer non-memory vector intrinsics. So those semantics are highly reusable, and it only costs about 2,500 lines of code to implement all those semantics. And so here you may ask, how does our synthesizer handle new instructions that has immediate constant in the right-hand side? For example, consider this rewrite as assume the enumerator generates this right-hand side for the left-hand side. The left-hand side is multiply percent A by 8, 16, 32, and 64. And assume the enumerator has generated this new right-hand side. What constant should we put in that operand? So should we explicitly enumerate all possible values for that constant? That might be too slow. And in our work, we relied on SMT solving again to synthesize those immediate constants in the right-hand side. There are multiple approaches for synthesizing immediate constants in the right-hand side. For example, Super uses counter-example-guided inductive synthesis or SIGs for this task. But in this work, we just encode the problem in the solver with a naive exist for all query. And we have observed that Z3 is quite efficient in this task. And basically, we're issuing the query like, does there exist a constant C, such as when substituted into right-hand side makes the right-hand side a refinement of left-hand side for all the input, for all the values of the input. And after the refinement check or the constant synthesis, we may have a valid rewrite, but we want to double check, is that right-hand side really cheaper than the left-hand side? Here, we need to use a cost model to check whether a rewrite performs better than the original program or not. And the LLVM IR itself is not a good choice here for predicting runtime performance. Instead, we compile both left-hand side and right-hand side to assembly, and then we call the LLVM machine code analyzer, and we check the number of micro operations required as the cost of our program. So here, I hope this covers all the details you need to know about our superoptimizer. And in the following slide, I will show a couple of examples followed by performance numbers. So this example is found when we use our superoptimizer to optimize Perl bench in SPEC CPU 17 benchmark suite. So in this top program, it tries to zero extend each lane in both vector from 8 bits to 6 bits, and then it calls the get average intrinsic on those two vectors, and finally it uses the trunk operation to convert the result back from 16-bit to 8 bits. And our superoptimizer is found that the round trip is not necessary, and the left-hand side can be replaced by just a SSE2 variant of the get average instruction. This rewrite reduces the cost from 4 micro operations to 1. And this is another example. So this is an handwritten kernel that swaps the endianness of a pair of 16-bit integers. The left-hand side is targeted for SSE2, and it has 3 steps. It uses, first it uses the shuffle vector to permute in the granularity of D word. And then it uses the funnel shift to swap in the granularity of a word. And finally, a B swap is called to do the final bit swap and byte swap. And our superoptimizer has found this pattern can be just replaced by a pchef call. By doing this, reduces the number of micro operations from 7 to 1. And also, another example. So although assembly operations are our superoptimizer's main focus, we also discover floating point and scalar optimizations. For example, this code from SPEC CPU 17 benchmark suite computes the differences between two floating point values and then checks if the result is greater than 0. It's perhaps surprising that LLVM, even a few months ago, cannot perform this simple optimization, which reduces the cost from 7 macro operations to 1. So this exact optimization has been implemented in upstream LLVM as a part of our work. So we have found many cases that an example optimization discovered by our superoptimizer seems to be broadly applicable. So we have reported many floating point and vector optimizations. So we compare the LibValueV with our superoptimizer, and this plot shows the speedup on the LibValueV test suite. And as I mentioned in the beginning of the talk, this library is heavily optimized by Chrome engineers. Yet we still got a significant speedups on this library. And this shows the SPEC 17 benchmark performance result for the SPEC 2017 benchmark suite. So the average speedup is about 1.5%, and the maximum speedup is 4.5 in one of the benchmarks. So with that, here I conclude my talk. So our superoptimizer is open sourced at this link, and thanks again, and I'm happy to take any questions.
I think we have time for 1 or 2 questions. Okay. Oh, question?
Hi, thanks for the talk and congrats on the award.
Yep.
So you said in the beginning that you are enumerating by complexity, so you're starting with constants and then increasingly more complex terms.
Yes.
Is that, are you just doing them one at a time? Like first you just try to enumerate constants, if it doesn't work, then you explore more things, or are you just doing it in parallel somehow? Like the enumeration, sorry.
So we create, first we create, constant, then, one instruction, right-hand side with one new instruction and then 2 instructions. And those are all generated before we send into the LLVM translation validator. Before that, we do a very quick short based on a approximate cost model that is just a summed weight of sum of the weighted. We assign each instruction a integer cost, then we sum on every instruction together. So this is our workflow right now. So there's a lot, of course, there's some room for improvement, but with current status, we're still,
Okay.
Yeah, skills very good.
Okay, yeah, real quick.
Sorry, I didn't mean to jump the line. Hi, I was curious. I'm Adrian Sampson. Hi, how are you?
Yeah, hi.
I was curious about the cut extraction step. I was just curious if are the extracted regions allowed to have uses outside of the regions? And if so, is that like does that influence the potential speed up? Like you have to keep around some of the instructions?
That is very interesting question. So we currently, in this work, we do not consider any external uses cases, but we may, so some other folks in my research group is working on, taking that into consideration.
Okay, let's thank the speaker again.